And it looks like we have another groundbreaking discovery in regards to gravitational waves, and specifically a discovery that, in theory, could solve a major mystery. The mystery of dark matter. But obviously, before we get too excited or before we actually start making new claims, I need to emphasize that this is a tentative finding and has not been officially confirmed and verified by other teams. But nevertheless, the implications based on the study we're going to be discussing are quite profound. And so let's talk about this new study and the new discovery in a bit more detail, because here a team of scientists from the MIT and a few European institutions released a study suggesting that we may have accidentally detected traces of dark matter that were hidden inside data from back in 2019. But whether this is true or not, this study, and obviously how everything in this case was discovered, may eventually change our understanding of the cosmos and how we see the universe itself. But first, I guess, let's discuss the basics and what we already know based on a lot of different observations. First, the mystery of dark matter. For decades, based on the observations around the universe, and based on what's actually seen in galaxies and galactic clusters compared to what's predicted, researchers realized that the entire universe seems to be dominated by these invisible forces, the dark energy and the dark matter. One of them, dark energy, causes the universe to accelerate its expansion. The other, dark matter, seems to hold galaxies and galactic clusters together. But as of 2026, no definitive particle or no definitive explanation for what's causing all of this has been found yet. And that's because, for example, dark matter is believed to be some kind of a particle that seems to only interact with matter through gravitational forces and nothing else. And so kind of like similar to, for example, a neutrino that only interacts gravitationally and using a weak force, here this particle might be even more invisible. But despite of this, for the past few decades, several experiments and several major observations try to find something. Now there have been some signs here and there, but as I said, nothing conclusive yet. But this invisible particle right now is still the best explanation we have. Nothing else explains all of the observations we see to such a precision. And so the question is, how do you find something you cannot see? Well, this is where black holes come into place. They're the perfect detectors. And that's because despite being black themselves, they are detectable through various means. And also because they are so massive and so dense, in theory they should be attracting a lot of these dark matter particles and possibly even trapping them in their own vicinity. But some of the most well-studied black holes are actually a result of a black hole collision. Essentially two black holes, several solar masses in mass, that rapidly start to approach each other in spiraling and then merging in mere seconds. And while during that final moment of the approach and the collision, they emit a huge amount of energy that's very often produced in a form referred to as a gravitational wave. Or basically it's a gravitational energy that can then be picked up by various detectors like LIGO right here on Earth. But previously, scientists assumed that a lot of these collisions most likely happen in vacuum, essentially empty space. Although some researchers also wondered what if these black holes are merging in some other region or possibly surrounded by a massive amount of dark matter. In other words, what if they're not really in a vacuum as much as the somewhat dense cloud of this very mysterious particle? This is referred to as a cloud binary system, and the system is also sometimes referred to as the gravitational atom. There's an older study in the description where you can learn more about this. But because we actually have no idea what sort of a particle this is, here scientists have to rely on various theoretical propositions, with one actually being kind of interesting. It's known as the scalar field theory. And in this proposition, there are types of particles referred to as light scalars, which would be extremely light in their mass and would actually be very difficult to find, resembling a kind of a background field as opposed to an actual localized particle. In other words, they would actually resemble waves and not really particles. And so at least one dark matter explanation uses these particles to try to explain all of the observable effects. But near a spinning black hole, that obviously would attract a lot of these particles, they can also extract some of the rotational energy through a process referred to as superradiance. You can learn about this in some of the previous videos, because this was a concept proposed decades ago, and has actually been observed around certain objects such as neutron stars and black holes. But basically it's a way to extract energy from inside the black hole. But for these types of particles around black holes, it results in this massive dense cloud of dark matter that wraps around these black holes and makes the binary act in a slightly different manner. And, well, this is what scientists sometimes refer to as a gravitational atom. It's essentially a black hole surrounded by this massive cloud of light scalar dark matter particles. And so because the black holes are merging inside this cloud, it also produces a kind of a cosmic friction. In other words, the black holes start to spiral in faster than they would in just empty vacuum of space. With this difference between expectations and observations should be observable as a tiny imprint inside gravitational wave detections. And well, if you were to graph this, it would kind of look like this. There's a very slight difference in collision speed and in the amount of time it takes these black holes to merge. And that's where this discovery from 2019 comes into play. Here at first, it seemed to be just a typical black hole collision that was not particularly interesting. It involved two black holes that then combined and produced a black hole of 20 solar masses in mass. So basically this was as average of a collision as you could get. But in this recent study published in the Physics Review Letters, researchers developed a new mathematical model that's able to predict exactly what this dark matter imprint would look like. And here they apply this to 28 separate observations with some of the clearest and most accurate data available to scientists. Or basically they picked 28 gravitational wave detections where the data was super good. And out of these 28 detections, 27 matched the previous vacuum model perfectly. But one of the signals did not. GW190728, detected on July 28, 2019. Because here when researchers analyzed the signal, they found that it didn't quite fit the standard vacuum model and instead showed a lot of preference for the dark matter environment model or the model involving a huge cloud of dark matter particles, with data specifically suggesting that these black holes merged while surrounded by a cloud of light scalar particles with a mass of approximately 10 to the minus 12 electron volts, which obviously would make them super light in mass and super difficult to detect. We don't actually possess any technology right now that can detect a particle that's so ridiculously light, which of course, if confirmed, would explain exactly why we're not able to see them. They're just too tiny. But right now, based on the statistical significance, this only has the sigma of about 3.5. Not 5, required to be a definitive finding, but still 3.5 is high enough to make this a tentative discovery that requires additional observations. So essentially this is a really interesting detection, but not a definitive sign of dark matter detection yet. And naturally, if this holds up and if there's additional evidence or additional calculations, it would officially provide the first time in history where dark matter has been detected on such a ridiculously small scale. But on top of this, it would obviously provide us with a brand new way to study the nature of these invisible particles without needing expensive detectors or machines underground. In other words, if confirmed, this would be groundbreaking. But there's also another important reason why this is so exciting: the accuracy. Because here researchers also realized that if we were to ignore these environments and assume that all of these collisions happen in pure vacuum, we in theory might be getting a lot of the black hole properties incorrect. And that's because for this particular collision, the vacuum model suggests black holes were much heavier and had more spin than they actually did. Or basically, the presence of these dark matter particles makes them look different from what they actually were. And so as one of the study authors put it, without models like this one, we could be detecting black hole mergers in dark matter environments, but systematically classifying them as having occurred in vacuum and with incorrect properties. And in reality, a lot of these collisions, assuming many of them did happen in this dark matter environment, would actually involve black holes that are just much different. But for now at least, that's I guess all we know. With the next question being, okay, so what's next? Well, obviously here first we need more data. And specifically by having additional detections in the future, and by collecting additional signals, some of the future detectors, including the Einstein telescope, may even be more sensitive to a lot of these tiny imprints, which will most likely result in one of two potential conclusions. Either something here was misinterpreted and this will be explained in some other way, or the dark matter particles were always here and this will allow us to calculate their exact properties and discover additional black hole collisions where they seem to play a large role. Although here are the other questions, of course. Okay, so if this one had these dark matter particles, why did the other 27 detections did not? In other words, why can we explain 27 of them as pure vacuum, And this one detection seems to be best explained with the dark matter cloud. So basically what makes these black holes so different. Either way though, for now at least, this detection and this collision is still going to remain a bit of a mystery and a kind of an outlier. So it's basically a potential echo of the invisible dark matter, but not a definitive detection yet. Nevertheless, this is still a very important first step in potentially discovering their true nature once and for all. On that note, once we discover something else, or once the scientists figure out what's going on in this case, we'll come back and discuss this more in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.